So next talk this afternoon is by Prasit Bhattacharya, who's talking from the University of Notre Dame, who's talking on equivariant cohomology operations and some relationship between squaring operations across fixed point functors.
Thank you. Thank the organizers for having me here. It's a pleasure and an honor to speak here, really. So as you can see from the title, I'm trying to develop equivariant squaring operations to start with. And these ideas, when I was writing down the abstract, I wasn't quite sure whether I want to give this talk or not, even though it fit very well. That's because the ideas were not fully developed and I didn't see how far I can reach. Nevertheless, this talk is going to be about the ideas which made me optimistic. I got a message, I guess I can, nevertheless. Okay. Okay, so as I was saying, some ideas that made me optimistic, and certainly I have been talking with Ming Kong, who is soon going to be in Bonn, and certainly in this talk, you are also going to see some of his ideas. So before I start, let me set up some conventions. My groups are going to be abelian groups of order 2 to the k, but maybe I can drop abelian in many cases. Oops. In many cases, but I just want to put it out there just for as a safety net. My field is going to be of order 2, and F2 underline is going to be constant G Mackey functor at F2. HF2 is going to be the corresponding Allenberg-MacLane spectra. And this is the Vieth ROG graded cohomology of a G equivariant space X, which is the homotopy class of equivariant maps from X to suspension V of HF2, where V is a element in the representation ring. And then the homotopy groups of my Allenberg-MacLane spectra is going to be denoted by bold M, and that's going to often play the role of coefficients. Okay, so.
May I ask a question,
yeah,
please, already? With this constant G Mackey functor, you have the fixed point functor and you have the fixed quotient functor. It depends what the restriction and the co-restriction do. Do you mean one of those, and which one?
So are you asking about this description?
No, going back to F2 underlined.
Yeah.
You describe it as a constant Mackey functor.
Yeah.
But I can think of two of them. One with restriction maps being 0, and the other with co-restriction maps being 0.
I think the co-restriction maps being 0.
Okay, thank you. Thank you.
Okay, so as you can guess from my notations, I'm sticking to prime 2. I'm doing a 2 primary talk, but that is just to avoid complications with odd prime. It just becomes difficult to describe. Some of these ideas does go through at odd primes. Okay, so let me describe my goals, what I want to achieve in this talk. I'm going to try to convince you that we can define G equivariant Steenrod operations. I would try to make some comparisons of squaring operations across various fixed point functors. And then the most importantly, I'm gonna parameterize my squaring operation using the either the homology or the cohomology ring of BG sigma 2 plus, which you can think of RP infinity with a G action. So in general, these gadgets are very difficult to, these cohomology rings are very difficult to calculate. The only very few cases are known, but my dream of this project is if someone computes the cohomology ring has enough description over here, then they can fit into my machine and get this Steenrod algebra immediately. So the slogan that I want to push forward is that if you understand RP infinity, or the cohomology of RP infinity, you understand Steenrod operations. So that's what I want to promote. From a slightly bigger perspective, if you have a map between the Ellenberg-MacLane spectrum, then automatically it gives you a cohomology operation from in the ROG graded cohomology of spaces. So in other words, these the G equivariant maps from HF2 to HF2 would be called the G equivariant Steenrod algebra. And I'm trying to maybe get, if possible, full information or maybe partial information about this particular algebra. So why is it an algebra? Actually, in the classical case, it's a Hopf algebra. So it has multiplication with some relations, which are Adam relations. And then there is Cartan formula, which is co-multiplication. These are something that I'm not there yet. I haven't fully explored the range of the ideas that I'm gonna next describe. But maybe I'll make some comments. Okay, so let me start by talking a little bit about equivariant analog of RP infinity. So by EG sigma n, I mean the total space of the principal G equivariant sigma n bundles, sigma n principal bundles, yes, and which is defined up to homotopy by its universal property, which is, so it is going to be a G cross sigma n equivariant space, such that when you look at a subgroup H of G cross sigma n, such that its intersection with sigma n is trivial, and you take the fixed point with respect to that, it's going to be contractible and empty otherwise for any other subgroup, which in particular means that sigma n or its subgroups sort of act freely on it. So the equivariant generalization of what we denote by E sigma n. Then BG sigma 2 is just going to be the orbits of EG sigma 2. This particular space has a very a nicer description. So let me just describe how maybe I'm gonna describe EG sigma 2. I can describe EG sigma 2 as a colimit of the unit in some representation that will be n times rho tensor omega, where rho is going to be the regular representation of G, and omega is going to be the sign representation of sigma 2. And then what you really want to do here is that you want to take the regular representations, direct sum of regular representations of G, and then you want to take the units there and identify the antipodes. This is that's why you take this as a model for EG sigma 2. So that's something you can do. Anyway, so these spaces are the G equivariant analogs of RP infinity, because as you can see, the underlying space is RP infinity. Let me talk a little bit about its cohomology, at least for some non-trivial groups that are known. The first group that I'm going to consider is C2, which is a calculation due to Hu and Krish in 2002. So first, let me describe the homotopy groups of HF2. It turns out that it's a polynomial in two variables, A sigma and U sigma, with added thing called the negative cone. Here is a picture. So here you can see this is going to be U sigma. This is going to be A sigma. So I'm using, so the x-axis is taking the total underlying dimension of your representation. And then, and this is, y-axis is counting the motivic weight, that is number of sign representations. So these live there. I haven't drawn the negative cone, but if I have to draw this, then I can just take this, copy, paste. Maybe I can rotate this, and then, oops. Maybe I'm not that good at handling iPad. The point is theta lives in degree -2 with these coordinates, and then there is a cone, which is the infinite divisible part. So that's the coefficient M when G is C2. And then the cohomology ring turns out to be free over M. It is generated by two variables, Y and X, such that Y square is, linear combination of Y and X. So it's A sigma times Y and U sigma times X. So I haven't drawn all the elements here, only the M2 generators in this picture over here. As you can see, it has two kinds of generator. One is this YX square, but then there is X square, and so on. It keeps going. It's a polynomial in X. So then from here, Hu and Krish also went on to describe the Steenrod algebra. Actually, he calculated the dual Steenrod algebra, and then closely related is a R-motivic Steenrod algebra, which was calculated by Voevodsky. Either way, you get the following answer, which is, oops, I just put an extra 2. So it is generated by square i's with modulo some Adam relations as usual. I'm not going to describe them explicitly, but the thing to note here is that the even dimensional squaring operation lives in I times rho, where this is the regular representation of C2. And then the odd dimensional guys lives in I rho minus one dimensional trivial. So these are the ROG gradings of the squaring operations. And one thing I would like to point out is that if you restrict your attention to just the even dimensional squaring operations and look at what the Adam relations look like. They exactly look like the Steenrod, classical Steenrod operations, just double of that. So something that I want all of you to keep in mind. So C4 was unknown until very recently. This is calculated by Nick Guarga-Coppolas, who is a student of Peter May in U Chicago. And he posted these papers in April. He did the following work. First of all, let me describe the coefficient ring M, which is both due to Nick and Ming Kong, who did it for Z, but calculations follow. Basically, this coefficient ring in C4 is extremely complicated. It has A sigma, U sigma. So there is always a generator with respect to some irreducible, two generators with respect to the irreducible representations. So sigma is the sign representation. So you got two. Then lambda is the rotation by 90 degrees. So you have A lambda, U lambda. And then there is infinite divisible guy. And then there is just like the C2 equivariant case, there is the negative cone. I didn't write it because, for a lack of better word, it's a mess. And also sort of not so relevant to what I'm going to talk about today. Anyway, so whatever is this coefficient ring, he also went on to calculate the cohomology of BC4 sigma 2. And he has a lot of different kinds of generators, e to the A, e to the U, e to the lambda, divided by, all these weird sort of things, and lots of relations, especially if you are trying to see its multiplicative structure. But additively speaking, or even multiplicatively speaking, what you notice is this, that there is an element called E rho, which generates a polynomial inside it with polynomial in M. So this is really curious. So this is you don't expect this to be free over M, but there is a sub thing inside this cohomology ring which is free and polynomial. Okay, and the result that we are claiming is that it is true in general. That is you're going to find a polynomial inside the cohomology ring of BG sigma 2 for any group G, two primary, any two group. What this generator is, this generator is going to be the Euler class of some equivariant bundle, which I'm going to soon describe. And once I describe it, you will notice that this Euler class, so basically Euler classes have this multiplicative property that Euler class of direct sum is just the cup product. So in this way, you are going to generate this polynomial inside this thing. Okay. Anyway, I'm going to come back to this bundle in a bit. But first, let me talk about a construction of classical Steenrod algebra operations so that you can see that it can be generalized equivariant.
Can I just very quickly ask a question? I mean, in the case of C2, there is this nice thing that you can sort of like not really talk about representations, but like translate into this motivic style grading, because we have sort of the preferred basis there somehow, right? The sign.
Yes,
So with
yes.
the C4, with the C4, it will be more difficult, right? I mean,
it is with C4, you have, you know, three-dimensional, because there are three reducible things.
But then you can do the tri-graded thing there, just and
yeah, you can, and yeah, I mean, you can, but soon as the order of the group generalizes, it becomes very difficult to visualize. But just to talk about this Euler class, you know, in the C2 equivariant class, I should point out the Euler class is here. So it is underlying dimension is 2. So it is in the regular, it is supposed in ROG graded, this is the row dimension, because this is one-dimensional sine and then two-dimensional total. That means one-dimensional trivial. So they add up to become regular in the case of C2. Okay. Okay, so so I'm going to philosophize the construction of classical Steenrod algebra. But before that, let me introduce a couple of gadgets which are going to be always there, which is the extended power construction of a space. So if you have a G space, a topological space with a base point and group acting on it, or you can take a genuine G spectra, then you can do this construction dng of x, which is nothing but you take this universal space, add a disjoint base point, and then smash over sigma n with x to the nth smash power, where sigma n acts on this by permutation. So this is the standard definition. And if you restrict G to trivial group, then, you know, when G is trivial, then I'm just going to write dn of x. Okay. Okay. So with this, I can quickly recall for everyone a construction of Steenrod operations. And this is sort of geometric in nature, where I see it and where I think I can generalize it to G equivariant case. So I would like to say that the Steenrod operations are a consequence of two important facts. One, that the Ellenberg-MacLane spectra is an E-infinity ring spectrum. And two, the tautological line bundle over RP infinity, which is often denoted by gamma 1, is HF2 orientable. Okay, so how so? Let me just point out that what A would give, because it's an E-infinity structure, you are going to get a sequence of maps. Let me denote them by theta n from dn, the nth extended power of HF2 to HF2, satisfying certain compatibility diagrams. And the important part is part B. So what does B going to give us? So if gamma 1, the tautological line bundle, is HF2 orientable, that means it cannot distinguish between the one-dimensional trivial bundle over RP infinity and the tautological bundle. So another way of saying this is there is a Thom isomorphism. That is, if you take the Thom space of, I said n times, well, you can choose n1 for now, but doesn't matter. Take the Thom space of n times gamma 1, smash it with HF2, and take the Thom space of n times the trivial bundle, smash it with HF2. These two are going to be weakly equivalent. So now I just want to point out this is going to be, you know, smash HF2. The right-hand side has a slightly better description, which is suspension n of the base space, which is RP infinity plus, and that's the usual Thom isomorphism we know. This Thom isomorphism, this is a standard fact, leads to leads to a Thom class, which is a map from the Thom space to the nth suspension of the Ellenberg-MacLane spectrum. And I should think of UN living in Hn of the Thom space. Okay, and I'm going to say that 1 plus A plus B leads to power operations, and power operations leads to squaring operations. So for every cohomology class U for an arbitrary space X, you can assign naturally an element which is called the power construction on U, which lives in D2 of X in the 2nth dimension. So before I describe this construction, a quick recall that D2 of Sn is by definition this smash product, this quotient, and sigma 2 is acting on it by swapping the factors. So this would turn out to be the Thom space of, let me just say, n times trivial direct sum n times the sign representation of sigma 2, and which eventually gives you this equivalence, that is, this is the suspension n of this Thom space of n-fold direct sum of gamma 1. Okay, now we are ready. So now what are we going to do? So I'm starting with the map U, which you can think of a map from X to suspension n of HF2. You can have D2 is a functor, so you can go from here to here easily. Then there is a natural quotient map. This is induced by the one way of saying this is induced by the diagonal map from E sigma 2 to E sigma 2 cross E sigma 2. These are spaces, so then you can take the quotient. And this is the weak equivalence we just talked about. And now here what you do, you take suspension n of your Thom class, smash with your theta 2, which theta 2 comes from the E infinity structure of HF2. And then, oops, something went wrong. And then you just use the multiplication of HF2 to land in 2nth suspension of HF2. So this composite, if I reduce the size a little bit, this composite is precisely an element in the 2nth cohomology of D2 of X. So that's your power construction. Now the next thing to notice is that, okay, so let sigma 2 acts on X trivially and X smash X by swap. And then it is very easy to see that the diagonal map is a sigma 2 equivariant map. So this leads to a map. Using the diagonal map, you get a map from E sigma 2 plus smash over sigma 2 X to D2 of X. And this, because sigma 2 acts trivially on X, there is this equivalence where B sigma 2 is your RP infinity. So in cohomology, this is going to be a map in the other direction from the cohomology of D2X to cohomology of this smash product. Now here you already have your Pn of U, and Pn of U is going to map to, because let me just say that, I'm going to denote B star of sigma 2 plus as the polynomial in T. Let's say I've chosen a generator. And then I can describe this this is going to be t to the I plus n tensor with something. That something I'm going to call the square I of u. And in this way, you can check that this assignment is natural by basically choosing u to be the fundamental class of Allenberg-MacLane spectrum. So once you do it, Allenberg-MacLane spaces. So in this way, you can define the classical squaring operations. But one thing I want to point out is that I made use of a Kunet isomorphism, which may not hold in general. Okay, so one has to be careful with. Okay, so then briefly speaking, the Cartan formula usually is a consequence of this sort of equation. That is, you consider a power operation on u, smash power operation of v, and pull it back along this projection map. And that's supposed to be the power operation of u smash v. And the Adam relationship is a consequence of some diagram like this. As I said, I'm not going to go into the details, but as I next describe the equivariant power operation and squaring operation, you can assume that equivalent equations would hold. Okay, so let's move on to G equivariant Steenrod operation in the same spirit. So the Allenberg-MacLane spectrum with coefficients in constant F2 Mackey functor is actually an E infinity G ring spectrum. So it's the correct analog of E infinity in the world of genuine G spectrum. So that's what it is. I'm going to give further description. And the second thing is that this bundle, which I am yet to describe, gamma G, is actually HF2 orientable. So what does E infinity G ring spectrum means? It means that I previously constructed for you what DNG, the nth G equivariant quadratic, extended power construction is. And all it means is that there is a map theta n from here to here, which is like sort of commutative which satisfies some coherent conditions to become commutative, to give you a G equivariant commutative multiplication. Anyway, the point is you have maps like this with some compatibility criteria. Now here is my gamma G. So let me focus on this first. So what you do to obtain BG sigma 2 is you take EG sigma 2 and smash over or cross over sigma 2 with the point. But now you can replace you can think of point as the trivial zero-dimensional representation, just zero. So I can write this as maybe point as 0, but I can also replace it by any G cross sigma 2 representation. And the G cross sigma 2 representation that I'm going to choose is the regular representation tensored with the regular representation of G. So this is the regular representation of G. And this is the sign representation of sigma 2. So let me make some remark. If you forget the equivariant structure, if you just look at what the underlying space is, this is supposed to be the order of G times gamma 1. That's the underlying line bundle, and order of G fold times because of this dimension of the regular representation. Rest remains same, right? That's how you're gonna. If you forget the G equivariance, then this becomes a trivial n-dimensional bundle. Now, Now I'm going to introduce another, which is analog of trivial bundle in the equivariant case, where I drop this sign representation of sigma 2 and look at just rho. Now, I claim when I say that HF2, when I say that gamma G is HF2 orientable, I mean that HF2 does not distinguish between these two bundles. That is because you can look at the fixed points and count, what bundles you get, and there is a corresponding thumb isomorphism on the underlying situation. So I'm going to get a thumb isomorphism from the thumb space of gamma G to epsilon G. And this thing so this is smash HF2, but this is suspension rho of the base space, which is BG sigma 2 plus. And I can also throw in some n if I like, right? So in the end, in the end, I'm going to get a thumb class, just like the classical case. And now the final observation that you need, which is analogous to the classical case, is that D2 of, let me just throw in some n here. So 1 point compactification of n times rho G, where sigma 2 acts by, so this is the description. Anyway, so sorry, I'm losing control over my iPad, which is sorry about this. The scrolling, maybe it needs some software updates, I think. So it has been bugging me for a week and I haven't done that. So now it's showing its true color. Anyway, the point is this thing analogously is the suspension n rho of n. So I can throw in n everywhere. And so this is the equation. And this is just a straightforward observation that D2G of S, 1 point compactification of n times sum of the regular representation is this suspension of this thumb space. Okay, now you can just mimic what happened classically to get the corresponding equivariant power operations. It's just happens exactly the same way. So I'm not going to go into the details of that. Oh, maybe I will. Okay, so here is the detail. So what you do, you apply D2 to your class U, which lives in the N row in the ROG grading. And then there are all these usual diagrams. You take the thumb class, smash the structure map of HF2, multiply, and you get a class. You get a class in 2N row. So one thing to note is that I have only constructed power operations for those ROG gradings which are multiples of rho. Now, the squaring operations. Now, as usual, if you take a G space, a space with a G action, and give X smash X a G cross sigma 2 action, G by diagonal and sigma 2 by swapping, and give X the trivial sigma 2 action. So this diagonal map is going to be a G cross sigma 2 equivariant map. So again, like the classical case, you can pull back along the diagonal this power construction on U to get an element in the 2n row-eth cohomology of BG sigma 2 plus smash X. Now, as I pointed out, the Kunet isomorphism may not hold, so which means that I cannot do this step, which creates some problem. But there is a way of bypassing it, which I'm going to talk very briefly. But let me just point out, in the C2 equivariant case, this is not a problem, because when G is C2, I described to you the ring structure on BG sigma 2 plus, which happened to be free over the coefficient. So which means that the warning that I just said does not apply to C2, but definitely applies to C4 or other groups. So now, okay, so for C2, when you do this, when you do the analogous construction for the squaring operations, you can describe, using Kunet isomorphism, you can express it in terms of, xn plus i's and yxn plus i's, and one of them is going to give you the even squaring operation, and one of them is going to give you the odd squaring operations. And let me just point out what happens to these squaring operations under two different things. One is restriction, that is when you forget the G structure or C2 structure, and one when you take the fixed point. So one remark I want to make first is that from here on, you basically define the Steenrod squaring operations, and what you need to do is learn what is going on the fundamental class of the corresponding Allenberg-MacLane space. I'm not getting into the details. These are some exercises one can work out. The other observation is that the restriction of the equivariant Allenberg-MacLane spectrum is the non-equivariant Allenberg-MacLane spectrum. So thus restriction gives you a map. Sorry about this. Restriction gives you a map from the ROC2 graded cohomology of X to the ordinary cohomology of the underlying space. And in a recent paper, which is joint with Guru and Ang Lee, we showed this, which is sort of expected. But we also studied what happens when you take, what happens with respect to the geometric fixed point, for example. Now here there is a little caveat. That is, the geometric fixed point of the Allenberg-MacLane, equivariant Allenberg-MacLane spectrum turns out to be this polynomial over HF2. But it's a disjoint union or wedge product, so you can always project onto the zeroth copy, which is a copy of HF2. And
but
with this,
strictly speaking, some suspensions are missing there, right?
Ooh, that's right. Thank you. Suspension I. Yes. So this is a connected. So you can, yeah, absolutely. Thank you. And then you can define a map from ROG graded cohomology of your C2 equivariant space to the ordinary cohomology of the fixed point of X. I'm saying fixed point because I said space. If it were a spectrum, I would have said geometric fixed point, because that's the one that commutes with suspension spectrum. Now there is another little thing, is that if you look at the C2 equivariant RP infinity and you take its fixed point, it's not quite RP infinity. It's a disjoint union of two copies of RP infinity. And you can actually work this out in terms of cohomology classes. So one way of writing this disjoint union is to pretend that this is B sigma 2 plus, let's say, smash S0 plus or something. Okay, so you just taking two copies, just adding an extra point. And its ring structure can be described like this. You have the usual, this is the cohomology of RP infinity, T is in degree 1, but then you add another generator in degree 0, call it iota, and then iota square has to be equal to, iota square has to be equal to iota. So that's the description. Now, under this map, so I have to tell you what happens on the coefficient ring. These are the things in M, these two, A sigma and U sigma. Under the functor induced by the geometric fixed point functor, A sigma goes to 1 and U sigma goes to 0. And Y goes to iota and X goes to T. But what you can also do, you can use the inclusion map of one of the copies, which corresponds to this T, let's say not iota times T, and then you can project it down to F2, Ft, and using this data, you can also compare the squaring operations across the fixed point functor. Sorry, this is again not moving as I want. Come on, move. Yes. And then we get the following description, that if you have the 2nth equivariant squaring operation and if you apply it to a class U and then take the geometric fixed point, then it is going to be the square n. So there is some sort of doubling process going on across the fixed point functor, which is sort of, for those who have seen this, should be expected. Let me give you a small application which we have in the paper with you, where we study fixed points, cohomology of or A module structure of various fixed points. But just to see an application, this is a good application which was also previously known, but can be explained using what I just told you. So take the mod 2 Morse spectra with the trivial C2 action and wonder what is going to be its cohomology, A module structure, or over the equivariant, what is going to be the A module structure of its ROC2 cohomology. So it turns out that it's going to be free over the coefficient ring, and then there are two cells. So I'm going to make another copy of this and place it maybe in degree 1. This is close enough. Now, in the underlying, I know that it has to be more spectra, right? So when I kill off all the U's, sorry, when I kill off all the A's, then I'm going to be left with these two things, and square 1 goes to square 1 under restriction. So there is going to be a square 1 here. But then the important thing is, it is also mod 2 Morse spectrum under fixed point, because C2 acts trivially. And because of the doubling nature, there is going to be a square 2 connecting these two. And this is just a very basic example. You can play this game in various cases and figure out what the A module structure of fixed points are going to look like. Anyway, let's move on to arbitrary group. I'm left with, I guess, less than 10 minutes. So let me handle the dirty case. when the Kunet isomorphism does not hold. So in this case, what I'm going to do, I'm going to pick up an element in the homology of BG sigma 2. I don't know what this ring is, but I'm going to parameterize my squaring operation using the elements over there. And let me pick a cohomology class in the n-roeth degree of the space X. Now I'm going to define for you the square lower t, not the upper t, but square lower t of u, which is going to be a class in 2n rho minus, so t belongs to actually v here, and these two v's are related. So what I'm going to do, I have actually a natural map, which is if I take the sphere SV, then I have this map T, because this is a homology, I will have a map T to HF2 smash RP infinity. And I carry X with the identity map. Then I apply my power construction, and something is off or what? No, I'm okay. Yeah. This is not quite. So there is a little bit of problem, which is I have to add a delta. I guess that's about it. The diagonal map, yeah. Because PU is originally defined from D2 of X until you, and this thing includes into D2 of X by the diagonal, using the diagonal map. Anyway, I get this composite. This composite, in short, is also called the slant product. So you can use the slant product to basically define this square lower t. And you can also, just by this definition, you can also check equations like this. For example, if I pick an m in the coefficient, it's going to the square lower t's are going to satisfy this rule. Now, let me go to classical case. In the classical setting, square lower t or square lower i's on a class in degree n is actually square n minus I. In other words, in order to define the square upper i's, you have to vary the index of your square lower things. And this is a slightly subtle thing. If you look at what square lower i's are, in this case, this corresponds to square beta i's, where beta I is dual to t to the I star, belongs to the homology of B sigma 2 plus. Okay, so these are the dual elements. Now, how to define them? I'm gonna not go ahead. As I said, I have some ideas how to make them upper and when can I make them upper. I'm not going to go into the details because my theory is not well found. My philosophy is, I'm not sure which is the correct way to do. I have a couple of routes which I haven't fully explored. So I'm going to leave it here with a cliffhanger and describe for you some conjectures which I think should be true. So I want to bring to your notice this thing that there is a polynomial algebra sitting inside the cohomology of BG sigma 2. So from there, I expect the following things to exist, which is there is going to be a squaring operation, which is going to be the order of g times some natural number n, going from Yeah, going from the which is going to increase the ROG grading by n row. So there is going to be a squaring operation like that. And there is going to be a quotient map from the equivariant Steenrod algebra to the basically this thing is going to be the 2 to the kth fold, the order of G, whatever is the log of order of G, that fold doubling of the Steenrod algebra tensor M. So that's a conjecture, but so for example, inside C2, you see the double of Steenrod algebra. Inside C4, you're going to see the quadruple of Steenrod algebra, so on and so forth. But this is because of the M2 free or coefficient freeness. I do not consider this as a good conjecture. The good conjecture is this, the third one, which is, let's pick a subgroup of G, which I denote by K. So if I restrict to K, then I know that it is going to be the Allenberg-MacLane spectrum again with K, action of K. So again, you can give a map like this from the in the RO G graded to RO K graded. And under this map, under the restriction map, the squaring operations are going to behave as usual, which is square order of G times N is going to remain order of G times N. This is just another way of writing order of G. But then if you pick a normal subgroup of G and denote by K the quotient group, then when you take the fixed point with respect to N, it is the categorical fixed point maps into geometric fixed point. So you're going to have a map like this. And because Allenberg-MacLane is a universal recipient sort of thing, I expect to have a map like this. I think Ming Kong convinced me. I have to ask again. So this is like, I don't know, last week conversation or something for last 2 minutes. I have 1 more minute left. So I'm just going to say that what I want to say is that there is some sort of fixed point functor that you can construct, hopefully. And under this fixed point functor, what it's going to do is going to reduce the order of the squaring operation, as I state here. So that's what I expect. And this is another conjecture. And with this, I'm going to end my talk. Thank you. Yes, exactly.
Comments?
Yeah, I just have one question. I mean, maybe this is a bit of a pretentious question, and I apologize for this, but
It really is.
but let's see if it is. I mean, I know you guys like spectral sequences, you and Mikong, and yeah, so there are several attempts in literature of doing this equivariant Adams spectral sequence type thing. Like the first one I know is actually due to Adams himself, and then John Greenleaf's PhD thesis, I think, does this, but it's based on Borel cohomology, and he sort of uses Siegel conjecture. And the thing with that is that it's useful, but somehow it ends up, again, because of all this Siegel conjecture business, to basically, like when you try to compute equivariant homotopy groups of sphere, just equivalent to doing Tom-Dick splitting and then separately computing everything. So does this kind of approach, if we do some Adams spectral sequence on Bredon cohomology, like what you are doing, and knowing now some of these operations, what you are trying to understand, is this going in this direction that we can actually run some Adams spectral sequence eventually, or is this not?
To run Adams spectral sequence, let me tell you that a lot of stars have to align. For example, you have to work with something which is half algebra, which it's not in the case of C2 itself. If not, then you want flat half algebroid so that you can calculate the E2 page. But what I think might be possible, if I have to be really optimistic from what I have right now, is that we are going to see glimpses of pattern from, because we are seeing some sort of double or quadruple of Steenrod algebra. So I don't know what it means. Maybe it highlights something along the, the chromatic fixed point theory along those lines. There is some connections there. I don't know. I don't know what it means.
For C2, that atom spectral sequence is already used by Hu and Križ in general in motivic.
Yeah, you can use, for C2, you can calculate a lot of different things.
But there is no example of somebody ever running this spectral sequence for C4, for example. At least
no, C4, there is no Steenrod algebra. The RP infinity was very recently figured out. So
I see. Yeah.
To be honest, these are great questions, but the state of the art is not there yet for us to explore like we do in case of C2 or classical.
Okay, thanks.
Are there any other questions? Comments? Not, we thank Prasit again.